He'll be speaking about outer automorphism groups of RAAGs and regular graph covers.
Okay,
Take it away.
thank you for the introduction. Okay, so in this talk, I'll introduce the automorphism groups of the right-angled Artin groups. And okay, so this class includes all automorphism groups of free groups and general linear groups over the integer rings. And so the most of this talk will be filled out by a mild introduction of the automorphism groups of right-angled Artin groups. But our result is a modification of Birman Hilden theory to the automorphism group of the right-angled Artin group with respect to the the simplicial covering maps. So this is joint work with Sang O and Philip Tranchita. So let's start. Okay, so to introduce the automorphism group of right-angled Artin groups, I need to start from the definition of the right-angled Artin group. Okay, so if you know the Artin groups, then the right-angled Artin groups. Okay, so right-angled Artin group is okay. So as a subclass of the Artin group, so the right-angled Artin group is the finitely presented group whose Coxeter matrix consists of only 4 and the infinity. So, where is the A? So in the finite presentation, so every relators are the commuting relations. So, but in the geometric group theory, there are 2 viewpoints. So the first is that we can consider the category of the right-angled Artin group as a finite simplicial graph category. So there is a functor A star. So we can define the right-angled Artin group by the finite simplicial graph. So if we choose a finite simplicial graph, then we can generate the right-angled Artin group by the vertex, and we can give a relations or whenever they are joined by an edge. Okay. Then the second viewpoint is much more the geometric. So we can think about that. We can think of the right-angled Artin groups as some fundamental group of some cellular complexes. So the complex is consists of the n-dimensional tri. So each torus corresponds to the free-abelian subgroup of the right-angled Artin groups. But we do not in this talk we do not think of the second viewpoint. So okay, so just focus on the first viewpoint. Okay, so yeah, so I think the first observation to study the about isomorphism of the right-angled Artin group is the isomorphism theorem. Okay, this was proved by the Laurence. Okay, he proved that the two right-angled Artin groups are isomorphic if and only if the two defining graphs are isomorphic. Okay, so the left to the right direction is very obvious because if we have a graph symmetry. So graph symmetry is just a graph isomorphism. So then the graph symmetry is a permutation of generators, and it also preserves the commuting relations. So the graph symmetry can extend. We can extend the graph symmetry to automorphism of the right-angled to an isomorphism of the right-angled Artin group. So it is very natural. Okay? But the non-trivial way is that the converse. So if we have an isomorphism between two writing the Artin groups, then we can. Okay, so the proof is very difficult. So but I will introduce just some concept of the proof. So okay, so we can take some we can compose to the given isomorphism we can compose okay, so sorry, so we can compose the inner automorphism and some partially inner automorphisms to the given isomorphism. Then we can assume that for every generator of the writing the Artin group of the gamma, so the image of the generator is cyclically reduced. So the cyclically reduced means that it has a minimal word length in the conjugal cyclists. Okay, then some by some technical method. So Laurence made bijections between the generators of the writing and Artin groups, and this bijection has a property that so each vertex of the lambda, so the image of the bijection, the f lies on the reduced word of the phi fu. So phi is the given isomorphism. So okay, so actually this condition finished the proof because the phi fu if two vertices of the gamma commute, then this implies that the two vertices of the lambda also commutes. Okay, actually this is due to the central Lighthouse theorem, but so there's some behind the theorem. So, okay, actually so we can finish the proof. Okay, so in the proof, the Laurence showed for types of the automorphisms. So in the automorphism groups of the writing the Artin group, there are 4 types of automorphisms. The first is the first type of automorphisms are the graph symmetries and the inversions. The inversions are the transposition of a vertex and its inverse. Okay, so V to the V inverse. Okay, then the graph symmetries are the permutation of the generating set, and they are all finite order, and they generate a finite subgroup of the automorphism group. So and the second is that we can also think about the complete subgraph of the gamma, and if K is a complete subgraph and if it has some nice condition, then we can take then K generates a free-abelian subgroup of the writing the Artin group because it is a complete graph, so every generators are commutes. Okay, so then if K has some nice condition, then we can take a matrix in the general linear group of the GK. So we can extend the matrix to the whole writing of the Artin groups. So the extension means that this is trivially X on the outside of K. So and the third type automorphism is also is a dual to the second. So if you so we can take the K in the complement graph of the gamma. So it means that K, the induced subgraph of K in the gamma is a edgeless subgraph. So K generates a free subgroup of the right-angled Artin group. Then if K also has some nice condition, then we can take an automorphism in the automorphism group of the K. Then we can extend this automorphism to the whole right-angled Artin group. Okay, so actually the second and in the second and the third type, the existence is not so difficult. So I mean we can define some pre-order on the vertex set of gamma, and this gives equivalence classes, and K is just it is one of the equivalence classes. Okay, and the last type automorphism is partial conjugations. Okay. Yeah, so we can divide the inner automorphisms into some partial conjugations. For example, if we think about the free group of sufficiently large length, then we can take a pair of generators. So in this case, we take A1 and AN. Then then we can construct some automorphism. So it fits the others, but conjugate the AN to the by the A1. So it sends the AN to the A1, AN, A1 inverse. Okay, then this is not an inner automorphism, so it is non-trivial in the outer automorphism group, but and it is of infinite order. Okay, so Laurence. Okay, so Laurence shows that so for every automorphism of the right-angled Artin groups, okay, it is a product. It can be expressed as a product of these four types of automorphisms. Okay, so do you have any question? Okay, so I will. That okay. So before I introduce our result, then I want to explain some important subgroup of the automorphism groups. So this was first developed by the Day and Wade. So if delta is an induced subgraph of the gamma, then delta generates a right-angled Artin subgroup of the whole right-angled Artin subgroup. Okay, so this is frequently called a special subgroup. Okay, so if you know the virtually special, then this is they are different. So yeah, so actually the virtual special subgroup can be virtually special, but the virtually specials are not a special subgroup. Okay, so okay, so Day and Wade define from the special subgroup. So so they define some relative version of the automorphism group overriding the Artin group. So if you arbitrarily choose two collections of the special subgroups, then they define the relative automorphism group by the collection of the automorphisms that preserves the special subgroups of G set Y's, and the fix the special subgroups in H the pointwise. Okay. Yeah. So because we take arbitrary collections, it can be empty, or it can be trivial, or it can be the whole group of the out zero A gamma. Okay, so out zero means that it is a finite index subgroup of the automorphism group. So just generated by the inversions and some elementary matrices, some matrices and the free automorphism groups and partial conjugations, except for the graph symmetry. Then because the graph symmetries form a finite subgroups, so the outer A gamma is a finite index subgroup of the outer A gamma. Okay. Okay, so this class, the class of the relative subgroup is very powerful. So they construct some subnormal series of the subnormal series of the finite length subnormal series of the automorphism group of the writing the Artin groups. Consisting of the relative subgroups, and each vector is has a finite classifying spaces. So they made or showed that the RFN always has a finite index subgroup whose classifying space is finite dimensional. So yeah, so and they made also showed that every relative subgroup generated by the 2, 4, 3 kinds of the generators, 2, 4, 3 kinds of the automorphisms plus the inversions relative to the collection of the special subgroups. Okay, so yeah, but our first result is very similar. So if we so our direction. So our direction is the O Philip and me. I and I's direction is finding another subgroup of the writing of the automorphism group. So we start from the simplicial cover. So if we consider the simplicial if you consider the connected graph gamma, then we can think about the covering space lambda, and the pi is a regular and the simplicial cover. So regular means that there is a back transformation, so whose quotient is exactly the gamma, and simplicial means a simplicial map. Okay, then we can define the asymmetry automorphism group and the lift automorphism group using this competitive diagram. So this pi, because this pi is a simplicial map, and there is a natural homomorphism between the A lambda to the A gamma. Then we can collect the automorphism, the fiber preserving the fiber preserving automorphism and the liftable automorphism. Okay, then they form two subgroups of the out A gamma and the out A lambda. Okay, so we say that this SOUT as the symmetric automorphism group, and the LOUT is as a liftable automorphism group. Then the first result is that the liftable automorphism group is also generated by the four kinds of the automorphisms, but automorphisms which are the liftable. Yeah. So as a remark, the liftable graph symmetry is very difficult. So it is NP hard in the combinatorics. So we don't know that what kind of graph symmetry liftable. But the 2, 3, 4, the 2, 3, 4. So I mean the matrices and the automorphism group of free, the extension of the automorphism group of free groups, and the partial conjugations. We can find some combinatorial characterization of the for liftability of each type. Yeah. So, but the LOUT. Okay. So, but the L. Yeah. But although the relative subgroup and the liftable subgroups are similar in the generating set, they have yeah, I don't know whether one implies the other. In fact, I believe there is no relationship between the relative subgroup and the liftable subgroup, because a liftable subgroup is much more symmetric in the graph. So yeah, just my belief. So we can. So because we start from the simplicial cover, we can apply the Birman-Hilden theory to the automorphism group of the writing the Artin group. So Birman-Hilden theory is that if we have a branch, a regular branched cover of the surface, then Birman-Hilden proves that there is some Schrödinger sequence between the symmetric Epping class group and the liftable Epping class group, and the transformation, the group of the transformations. But our case is some different. So the kernel of the SOUT to the LOUT can be infinite. So it has more than the transformations. So, but O and I and the Tranchta showed that. So the other part of the deck transformation is always a Trolley elements. So the Trolley elements is a Trolley elements are the automorphism whose homological representation is trivial. So yeah, so actually so in the first term the product of the deck transformation and the subgroup of the Trolley subgroup is actually the semi-direct product of the we can express them as a semi-direct product, because the Trolley element is the Trolley subgroup is a normal subgroup of the automorphism group. So yeah, so this is exactly the semi-direct product, and And yeah, this is and I want to introduce some study of the writing Artin, some automorphism group of the writing Artin group. So the automorphism group of a writing Artin group share some properties. So they are residually finite, and they satisfy the teach alternative, and they has a finite virtual cohomological dimension. Okay, so that was proved by the Charney and Vogtman and the other the Day and Seo ways and the crisps. Okay, then, but the RFN and the general linear group is very different. So actually, the RFN is acylindrically hyperbolic, but the general linear group is not, is a boundedly generated. So Guerrero and Seo discovered the some dichotomy in the of the class of the automorphism group of the writing group. So one part is consists of the RFN, and the other part consists of the general linear groups. So the part containing the RFN satisfy the some vastness properties. So Guerrero and Seo showed that this part satisfy the no bounded generation and the SQ universality, and they have infinitely many quasi-morphisms. Okay, so if you want to study the automorphism group much more geometrically, then you can also think about the deformation spaces. So that was developed by the Charney and Vogtman and the Crisp and Stambach and Bregman. But there's the Bregman talk in Paris in the last month. So he asked to the I don't know. So what is the okay? So listener, I don't know. So whether he wants to develop some a nice boundary of the deformation space of the writing guard, the deformation space of the automorphism group, outer space of the writing Artin group. And you can also study the cubical geometry. You can also study the automorphism group using a cubical geometry. So actually, this is very recent research. So the Fioravanti studied the coarse medium preserving automorphisms. So and the so for writing the Artin group, the coarse medium preserving automorphisms are all untwisted. So and the Geneva focus on the on just the automorphism group of the writing the Artin group, but yeah, his result is very fancy. So he classified all conditions for the epsilon-liquid hyperbolicity of the automorphism group of the writing the Artin group, and recently, actually, I don't know. I haven't read this paper, but recently the Brock developed some generalized free-vector complexes. So yeah, so there's some many structures similar to the free-vector complexes. So for example, there's some so every complex is from the writing the Artin group is homotopically equivalent to the wedge of the spheres. So okay, so yeah, and thank you. Thank you for the listening.
Thank you for your talk, Donggyun. Does anyone have any questions? Well, if there's no questions, let's thank Donggyun again, and we can move on to the next talk.